So in 7.4, we want to see how differential equations relate with exponential growth and decay. One of the models for the population growth that we considered in section 7.1 was based on the assumption that the population grows at a rate proportional to the size of the population, which is dp over dt, which is equal to k times p. Now, is that a reasonable assumption? Suppose we have a population of bacteria, for instance, with size p is equal to 1,000, and at a certain time it is growing at a rate of p prime, which is equal to 300 bacteria per hour. Now let's take another 1,000 bacteria of the same type and put them with the first population. Each half of the new population was growing at a rate of 300 bacteria per hour. We would expect the total population of 2,000 to increase at a rate of 600 bacteria per hour initially, provided there's enough room and nutrition. So if we double the size, we double the growth rate. So in general, it seems reasonable that the growth rate should be proportional to the size. The same assumption applies in other situations as well. In nuclear physics, the mass of a radioactive substance decays at a rate proportional to the mass. In chemistry, the rate of a unimolecular first-order reaction is proportional to the concentration of the substance. In finance, the value of a savings account with continuously compounded interest increases at a rate proportional to that value. So in general, if y of t is the value of a quantity y at time t, and if the rate of change of y with respect to t is proportional to its size y of t at any time, then we have equation 1, which is dy divided by dt, which is equal to k times y, where k is the constant. Now in this equation, it's sometimes called the law of natural growth if k is greater than 0, or the law of natural decay if k is less than 0. And because it is a separable differential equation, we can solve it by the methods of section 7.3. So what we're going to do here is we're going to divide both sides by y and multiply both sides by dt, and then we're going to integrate both sides. So we end up getting the natural log of y, which is equal to k times t plus c. So rewriting this using logarithmic properties, we have the absolute value of y, which was equal to e to the kt plus c, and we can rewrite that as multiplying each base with the exponent. So this e of c, or e to the c power, is going to equal a constant, so we're going to call that a. So here we have y is equal to a e to the kt, where a can be equal to plus or minus e to the c, or possibly 0, is an arbitrary constant. So to see the significance of the constant a, we observe that the y of 0, which is equal to a times e to the k times 0, which would just give us a. And therefore, we can then say that a is the initial value of the function. Now, because equation 1 occurs so frequently in nature, we summarize what we have just proved for future use. So for equation 2, the solution of the initial value problem, dy over dt, which is equal to k times y, where we have y of 0, which is equal to the initial value of y, is the following function, y of t, which is equal to the initial value of y, times e to the power of k times t. Now with population growth, what is the significance of the proportionality constant k? So in the context of population growth, then we can write equation 3. So if we have dp over dt, which is equal to k times p, then we can divide both sides by p. So we would have 1 over p times dp over dt, which is equal to k. And that quantity, 1 over p times dp over dt, is the growth rate divided by the population size. And it is called the relative growth rate. So according to equation number 3, instead of saying the growth rate is proportional to population size, we can say the relative growth rate is constant. So then equation 2 says that a population with constant relative growth rate must grow exponentially. Notice that the relative growth rate k appears as the coefficient of t in the exponential function y naught times e to the power of kt. So for instance, if we had dp over dt, which is equal to 0.02 p, and t is measured in years, then the relative growth rate is at k, which is equal to 0.02. And by converting that to a percentage, we can say that the population grows at a relative rate of 2% per year. So if the population at time 0 is p sub 0, or the initial population, then the expression for the population is the following. P of t, which is equal to p of 0, which is the initial, e to the power of the constant 0.02 t.